Hey, what's up? This video is about simplifying radical expressions. I'm going to give 4 examples because I believe each of which illustrates a particular, slightly different type of problem that you'll run across. So the first one I'm going to start off with is just a simple root 40. And what we're supposed to do is we're supposed to simplify. What they mean by that is they want you to try to pull out factors from this square root sign. So the way you do that is the first thing you do is you break down 40 into its constituent factors. So all you do is you just start thinking of numbers and multiply together to make 40. Well, I could think of 8 and 5 would work, 4 and 10 would work, so it doesn't matter which one I use. I'm just going to pick. Alright, 4 and 10. Alright, then for each one of these numbers, I think of 2 numbers that multiply to make that number. So I'll go like this, 5 and 2. See how 5 times 2 is 10. 4 times 10 is 40. I'm just working backwards, making a tree. It's called a factor tree. So how about numbers that multiply to make 4? Well, 2 and 2. Okay, so what this is called, 2 times 2 times 5 times 2 is called the prime factorization of 40. So this is actually going to help me to simplify it. So what I'm going to do is I'm going to rewrite root 40 as the square root of 2 cubed times 5. Now, why did I do that? Because do you see how I have 3 2's and 1 5? So there's 3 2's and 1 5, because this is really 5 to the 1. So, because if I went 2 times 2 times 2 times 5, I would get 40, right? Because isn't 2 times 2 times 2 8, and 8 times 5 is 40? Yeah, absolutely. So, because that it works out because I did my factorization correctly. So, now, you're kind of wondering probably, why did I write it this way? Alright, well, the reason I did is because now that I have it 40 broken down into its prime factors, I can know what to pull out. Oh, and by the way, the reason they're called prime factors is because 2 and 5 are both prime numbers. You see what I'm saying? Do you see how you have to stop factoring down here when you get down to a prime number? Because the definition of a prime number is that it doesn't have any factors besides 1 in itself. And so that's why you stop when you get to the prime numbers. But anyways, that's a side note. So I'm here, what I just did is I just took this root 40 and I rewrote it as the root of 2 cubed root 5. So I just rewrote 40 as this. So this is useful. Now keep in mind, you know how a square root has an imaginary little 2 here. Okay, they don't write it very often, but it really does. So what that means, this number right here is going to tell me the size of the group of the factors which I'm going to pull out. So notice, you see how in here I have 3 2's and 1 5. So if I took out 2 of those factors of 2's, I would be left with, or actually, if I broke up 2 of these factors of 2's, I could rewrite this as 2 squared times 2 times 5. So what I'm going to do, if I take the square root of a 2 squared, that's just the same as 2. So I'm going to take this 2 squared and pull it out, and it's going to become a single 2 out in front. And so my answer is going to be 2 root 2 times 5, which I can write more simply as 2 root 10. So let me just give a real quick overview of what I did here, because I feel like somebody's going to be lost right now because I went pretty fast. So what I did, I took root 40, I broke it down into its prime factors. Using those prime factors, I rewrote 40 as a product of its prime factors. So because there was 3 2's and 1 5, that's why I have 2 cubed times 5 to the first. Alright, then I said, okay, because it's a square root, and there's a 2 here, what it means is I'm going to be pulling out pairs of 2 factors. And so I recognize that 2 cubed is the same as 2 squared times 2 to the 1 times 5. And then this group of this 2 cubed, it gets pulled out of the factor, it gets pulled out of the root sign, and it becomes just a 2. Because if I took the square root of 2 squared, it's just 2, right? So this is what I ended up with. Now, the reason the 2 is outside of here, the reason why there's a 2 and a 5 in here, is because that is what was left when I pulled out this 2 squared. And so I just rewrote it by multiplying back together these 2 factors that I can't take out, and I finally got 2 10's, or 2 root 10. So that was the that's the process. Now, this is a simple case. I'm going to show you another one. All right. What if you had something like root 77? So this will be like problem 1, this will be like problem 2, okay. So root 77, I'm going to do the same method. I'm going to break it down. I'm going to say, okay, what are two things that multiply to make 77? Well, 7 and 11. So I can rewrite root 77 as the root of 7 times 11. Now, the problem is here, is you see how I don't have a pair of 7s, and I don't have a pair of 11s? Because I don't have a pair of either one of these factors, I can't do anything. Meaning that root 77 is fully simplified. There's nothing you can do about it. So I wanted to show you this example because it illustrates the fact that the only time in which you can simplify a radical is when you have at least, simplify a square root is when you have at least pairs of factors and not just single factors. So I don't think I'm explaining it very well, but maybe you could see from what I'm writing down. So I have two more examples. Here's a third example. It's if you have something like this. What is the cube root of 54 written in a more simplified format? So I'm going to do the same thing. I'm going to first start off by breaking down 54 into its constituent prime factors. So two numbers that make 54. How about 27 and 2? 27 times 2 is 54. Alright, how about numbers that make 27? I can think of 9 and 3. Alright, how about numbers that make 9? 3 and 3. Okay, so I'm done, because these are all prime numbers. 3 is a prime number, and 2 is a prime number. So I'm going to do the same thing I've been doing. I'm going to rewrite this problem. Instead of the cube root of 54, I'm going to rewrite it as the cube root of 3 cubed, 3 to the third, because I have 3 3's, times 2, because I only have 1 2. Alright, now notice, and now, whereas before I was pulling out pairs of factors because it was a square root, now since it's a cube root, meaning there's a 3 here, I'm going to be actually pulling out triplets of factors. So what that means is that this 3 cubed is going to come outside and just become a 3, because the cube root of 3 cubed is 3. So then I'm going to rewrite this as 3 root 2. Did you follow that? It's a little tricky. Basically it's just if you're going to do an overview here, it's because you have to consider that the number here, I call it the index number. I don't know if that's actually the name, but I call it the index number, whether it's a cube root or a square root. This is the number that indicates the number of factors which must be in a group in order for them to be pulled out. So I pulled out the 3 cubed and I was left with the 3 root 2 because 2 was the only number that was left inside when I took out the 3. So that was example 3. It just shows what happens when you have something that's not a square root. By the way, what if it was a 4th root? Well, I would pull out things to the 4th power. If it was a 5th root, I'd pull out things to the 5th power. So meaning that I would have to have a group of at least 5 factors to pull it out if it was the 5th root. So just try to get that idea in your head. Okay, it's very easy to think that sometimes you always pull out pairs because people are used to square roots, but it's always you have to look at this number and make sure. So all right, the 4th example is when you want to use this idea of simplifying radicals to simplify an entire expression. So let's say I had something like this. How about root 12 plus root 75. Now on the surface it looks like you can't do anything to further simplify this expression because root 12 and root 75 are not like terms. It would be like trying to combine an x and a y. You can't do it. So what I'm going to do is I'm going to use this process which we've been doing to rewrite 12 and rewrite 75, and then something might happen. So you'll see what I'm talking about. So let's start with 12. Okay, so numbers that make 12. 3 and 4. Alright, factors that make 4. 2 and 2. Alright, so now we're going to do 75. How about 25 and 3? Okay, 25. How about 5 and 5? So, using these factor trees, I'm going to rewrite this problem using in the prime factorization mode, okay? So instead of root 12 plus root 75, I'm going to have root of 2 squared times 3, because of this factor tree, 2 squared times 3, plus 5 squared times 3. Because I have 2 5s and 1 3, so 2 5s and, times 3. Okay, so again, so what's the next step? Remember, since this is a square root, these are both square roots, I'm going to be pulling out pairs of factors. So I'm going to pull out, I'm going to rewrite this, I'm going to pull out this pair of 2's. Comes outside the radical, it just becomes a single 2 because I took the square root of it in the process of pulling it out. So this is a 3 plus pull out a pair of 5s. This is a 5. Root 3. Hey, check this out. Now look at this. This conveniently, actually, I designed the problem this way, but the point is, when you factored it, now these are both root 3s, so they're like terms. So this is just 2 root 3 plus 5 root 3, so the answer is, as you might guess, 7 root 3. So there you go. So what that means is that root 12 plus root 75 is exactly equal to 7 root 3. If you don't believe me, you can try it on your calculator, but I can assure you that assuming we did all of our math right, then that has to be the answer. And this is actually a very useful thing to know how to do when you're solving and you're simplifying, you're trying to solve equations, because it allows you to combine things that don't, although they don't appear like terms, they actually are. So that was basically it. That was kind of a long and rambling video, but I hope you got something out of it, and thanks for watching.